Black holes might just be one of the most fascinating and mysterious phenomena in the universe. They are massive beasts in terms of power, but at the same time virtually invisible to us, with a black hole potentially weighing 2 to 4 million times the mass of the Sun. However, due to the research put into them over the last few decades, we've gone from knowing absolutely nothing about them to learning more and more up close and personal. Recently, Michio Kaku announced that we finally got a look at what's inside a black hole, shedding light on details the world of science might have missed all along. Space is vast and complex, but before we dive into the specifics of Kaku's findings, it's essential to discuss the basics. Although most people have some idea of what black holes are, there are still gaps in the right information. In 1916, Albert Einstein published his theory of general relativity, predicting the existence of black holes. At that time, the concept was purely theoretical, and it took another 50 years for the scientific community to find evidence of their existence. In the 1960s, astronomers studying the Cygnus constellation noticed an oddly bright blue star emitting X-rays, which was not stagnant but orbiting a giant black object. Further investigation revealed that the X-rays were being sucked into this black entity, confirming it as a black hole. This discovery was significant, providing proof that black holes exist and are not just figments of Einstein's imagination. Researchers named this black hole Cygnus X1, located about 6,000 light-years from Earth. It was a major discovery, being 14 times brighter than the Sun and incredibly dense, with a strong gravitational pull so intense that even light cannot escape, hence the term black hole. The concept of a black hole is both fascinating and terrifying. It is a region of space where gravity is so strong that nothing, not even light, can escape. Anything that gets too close will be pulled in, never to be seen again. This aspect of danger makes it even more necessary to learn everything there is to know about them. Following the discovery of Cygnus X1, scientists started searching for other black holes and found that there might be over 100 million black holes in the Milky Way alone. However, because they are incredibly hard to detect, we still do not have an exact number. From the looks of it, there are several million black holes in our galaxy, making their study even more important. The main concern with black holes is always going to be gravity. Their gravitational pull is so intense that anything entering them compresses down astronomically until it becomes a singularity. In simpler terms, black holes are like cosmic vacuum cleaners that suck everything in. One of the scariest parts about black hole research is the fact that if someone were to fall into one, they would be stretched to the point of becoming a single line, dying before the final form sets in. Therefore, no one should step into one, but the proximity of black holes still raises questions and concerns. In 2021, scientists released the first clear photograph of a black hole, specifically the M87 black hole, captured over several nights. By stitching individual photos together, they gathered more evidence and discovered that black holes have 3 layers. The first layer is the event horizon, the point of no return. The second layer is the photon sphere, where light orbits the black hole and cannot escape its gravitational pull. The third layer is the singularity, where everything entering the black hole gets compressed down astronomically until it becomes a singularity, a point in spacetime where the laws of physics break down. Studying black holes is challenging because each one is unique, and the traditional methods of scientific inquiry don't apply. Scientists can only study black holes indirectly by observing the radiation they emit and the gas and dust surrounding them. Sending a probe inside a black hole is impossible, as anything entering the event horizon is pulled towards the singularity and compressed to an infinitely small point. This means scientists are left studying black holes in a two-dimensional way, despite their three-dimensional nature. Another compelling theory is that black holes are created from collapsed stars. When a star exhausts its fuel, it can no longer produce enough energy to counteract the force of gravity, causing it to collapse in on itself. If the star is massive enough, this process continues until it becomes a singularity. NASA scientists observed a super-powerful whirlpool of super-hot hydrogen gas at the core of the M87 galaxy, spinning at an astonishing rate. They deduced that a colossal mass, weighing as much as 2 to 3 billion suns, was preventing it from flying apart, confirming it as a black hole. In 1963, New Zealand mathematician Roy Kerr used Einstein's equations to describe a spinning black hole, which wouldn't collapse into a point but into a ring of fire or a thin disk. This spinning disk of matter, called the ergosphere, surrounds the black hole where the laws of physics break down. Kerr's solution also predicted the existence of an Einstein-Rosen bridge, or wormhole, a theoretical passage through space-time that connects two separate regions of the universe or parallel universes. If someone were to fall into a black hole, instead of being crushed, they might be sucked through a tunnel and shot out of a white hole in a parallel universe. Wormholes are a prediction of general relativity, but they are inherently unstable and would collapse almost immediately. The idea of black holes and wormholes as pathways to other parts of the universe or different times has fascinated physicists for decades. The concept of the Kerr wormhole, named after mathematician Roy Kerr, is visualized as a ring-shaped portal, like the looking glass in Alice in Wonderland, transporting a traveler to another universe or time. While exciting, the idea of wormholes as a means of interstellar or time travel is controversial. Critics argue that wormholes might be unstable or impossible to traverse due to intense radiation and subatomic forces. To truly understand these phenomena, a new theory is needed that unites gravity with quantum theory, known as a theory of everything. Renowned theoretical physicist Michio Kaku has been working on such a theory for decades. The most promising version is superstring theory, which unites gravity with the quantum theory. This theory proposes that subatomic particles are tiny vibrating strings, and that the universe is a symphony of these strings. As strings move in time, they warp the fabric of space, producing black holes, wormholes, and other exotic solutions of Einstein's equations. However, the extra dimensions of spacetime required by superstring theory are so small that they can't be studied directly. These dimensions might be curled up tightly, like a sheet of paper rolled into a cylinder. Alternatively, the extra dimensions might have been more visible during the Big Bang, but collapsed as the universe expanded. The mathematics involved in superstring theory is incredibly complex, opening up new areas of mathematics previously unexplored. Despite the challenge of solving the problem of a quantum black hole, some physicists believe it is only a matter of time before someone cracks this problem. Until then, it's too early for intergalactic or time-traveling expeditions. The problem of infinite answers in string theory isn't unique. Many great theories have infinite solutions, requiring initial conditions to predict motion. For string theory, these initial conditions are the Big Bang itself, which are currently unknown. This means that to fully understand the implications of string theory, we need to define what we are describing. Unlike other theories, the initial conditions of string theory trace back to the Big Bang itself. This requires specifying the conditions at the instant of creation, which remain elusive. String theory continues to evolve, promising new insights into the nature of black holes and the universe. It introduces the concept that subatomic particles are not points but vibrating strings, suggesting that the universe is a symphony of these strings. Each string vibration corresponds to different particles in nature, offering a unified framework that could explain the mysterious phenomena observed in the cosmos. However, the challenge remains in reconciling string theory with observable phenomena and experimental data. While it has sparked new mathematics and theoretical frameworks, the actual detection of strings or extra dimensions remains beyond current experimental capabilities. Theoretical breakthroughs, such as resolving the quantum behavior of black holes within string theory, are ongoing endeavors that may one day shed light on the deepest mysteries of the universe. In conclusion, while black holes and wormholes captivate the imagination with their potential as gateways to other realms of spacetime, their true nature remains a subject of intense research and speculation. String theory offers a promising avenue for exploring these phenomena, but requires further development and experimental validation to realize its full potential in understanding the universe.